Good morning, Tasneem. How are you?
I'm doing well. How are you?
I'm great. I'm great. Time does fly.
It sure does. Can you believe it's already day 2? Yesterday was incredible.
Absolutely. It was a fantastic start to what promises to be an exciting conference. We had a day full of engaging activities, from the opening ceremonies to the keynote presentations, as well as immersive exhibitions and panel discussions. It did not disappoint.
Definitely. From advanced manufacturing to renewable energy, the insights we heard yesterday were nothing short of groundbreaking.
And with so many networking opportunities, we saw how students, researchers, and professionals from across various fields connected over shared ideas and goals. It was a great way to kick off the conference.
For sure. And here we are, already on day 2. We've had such a great start, and today promises even more exciting sessions. But before we officially get started, we want to take a moment to officially welcome all of you back. Thank you for being here. And if you're joining us for the first time, welcome to the Global Student Research Conference, JISR 2025. My name is Tasneem Al-Atrash. I'm a sophomore finance student at KFUPM, and it's a great honor to be one of your Masters of Ceremony today, alongside...
I'm Ali Shakrawa, and I'm a master's student at the Department of Geology. It's a great pleasure to have you all with us today. For those who may be new to JISR, allow me to share a bit about who we are. Global Students Research, JISR, bridges the gap between students, researchers, and professionals from across various disciplines. We bring together STEM and business fields to collaborate, share ideas, and tackle the most pressing challenges of our time.
Exactly. At JISR, we provide a dynamic place for students to come, elevate their skills, share innovative ideas, and connect with experts in the fields. Our mission is to empower the next generation of leaders through immersive workshops, inspiring keynotes, and collaborative sessions.
Definitely. And this year's theme, Disruptive Technology, explores how technological advancements are reshaping industries all across the globe, whether it's robotics, artificial intelligence, or sustainable solutions. JISR offers the opportunity to dive into these innovations and see firsthand how they're transforming the future.
And we're excited to continue the conversations today. We have a full agenda packed with more amazing speakers. So without further ado, let's welcome our first speaker, Dr. Abdul Muhsin Al-Hamam, lead of biotechnology research at Aramco. In his session today, he'll be exploring how sustainable biotechnology is solving problems in upstream petroleum operations. He'll share how these innovations are shaping the future of the oil and gas industry. Please join me in welcoming Dr. Abdul Muhsin.
It's not working. What about now? But I'm not seeing anybody back there say he hearing me or not. Okay, good. Good morning, everybody. It's my pleasure to be here and standing in such great university and with the very strong and empowering students who is running such amazing conference like today. And from here, just giving me a pleasure to stand and talk about one of the area that is really great and have really impacting in the oil and gas industry, just moving little bits with the different flavors than usual. Biotechnology. And as we are talking about the biotechnology and the sustainabilities nowadays, we are having a sustainable solution by the applying of biotechnology within oil and gas industry. And from here, I'm trying to, I don't know. To talk about what is the definition of the biotechnology before we move on the application? Biotechnology is what they call it, the use of living organisms in manufacturing processes to create a product and solving the problems. That means we're trying to find a platform that we can utilize it in a different industry, in the food industry, health industry, manufacturing some of the medications, and now in oil and gas industry. So basically, it is a tools and platforms that we can manipulate and using it for our purpose and our application. And with the advancements of the biotechnologies tools, as we can see it over here, the sequencing, genomics, bioinformatics, and bioengineering, that give us really great tools to move and tween the things for our application. So with this, we agree and we have understanding what is the biotechnologies. So from here, we try to see what is their application oil and gas industry. Okay. As you can see over here, in 2013, a literature paper has been published with the complete overview about the biotechnology and petroleum industry, and especially about the upstream. When we are talking about the upstream in oil and gas industry, we are talking about the underground. Any operationals, processes, when we call it the upstream, that's mean under the grounds. And downstream, which is any processes, any plants, refineries, they call it downstream. So in this paper, spotlighting in many applications in oil and gas industry, which is the biopolymers production. When we are talking about biopolymers, which is they call it a polymers that using during the drilling processes. During the drilling, that's biopolymers making really great efforts by cooling the bit during the drilling. First. Second, making like a cakings in the site and holding the formation from and the sand from healing down to the during the processes or during the drilling. So this is one of the application. Second, about the drill breakers. When we are drill and after the drilling, we try to make a fracturing within the downhole to enhance the production, to enhance the oil to get in. That fractures, to keep it remaining and to make the oil coming out, we are filling with the gel. That gel is basically extracted with some from the bacteria or strain of bacteria to be modified or producing that gel. In addition to that, the biocatalyst, and you name or you can highlight how important the catalyst in oil and gas industry. So we can generate a biocatalyst from the bacteria. In addition to that, in the in situ about the biosurfactant and the biodesulfurization, removing the sulfur from the oil itself. Now, one of the hot subjects in oil and gas industry, and that's give us really a proud of using it as one of the main product. Plus the biosurfactant and the surfactant and the importance of the surfactant in the industry, that give us also additional impact. And I can say a lot of the bioremediation, etc. There is a lot of things that's happening and a lot of, application. And that paper has been spotlighting, which shows the huge potential about that knowledge or that biotechnology. In addition to that, in one of the prestigious journal, GPT, which is Journal of Petroleum Technology, and their cover page, in May 2016, there is what they call it, photos worth million words. That means the involvement of the biotechnologies and from the exploration from the surface of the ground during the drilling, during the production, and involvement of the biotechnologies from the zero or from the ground up to the reservoir of the oil until back to the production of the oil. So a huge potential of application of that processes in oil and gas industry. So we need to understand what is the problems and the challenges oil and gas industry have so we can design our application or our technologies as based in bio to fit and to address these problems and finding a solution for these problems. And as you can see it, from these problems, the fracturing and completion optimization, as I highlighted, fracturing, sometimes with when they do these fractures, they need the gel to make it filling that fracture from being closed. Also, sweet spot identification. When I was saying a sweet, doesn't mean it's a sweet to eat it. It is selection, the zone where is the oil is there. They call it a sweet as like an oil spot and zone that we can target it. So that means we're going to produce out of that spot. They call it sweet spot. Also, when we during the drilling, what we call it, we have a water production from different zone coming that interrupts the processes of drilling, and we don't need it. We need to close it. Also, we have what they call it, the drilling fluids. Some of the drilling fluids happening, it has starch, and that starch is based on, it utilizes as a nutrient for some of the bacteria, especially when we are using the water during the drilling, and that water is not being treated with the biocides or treated from or sterilized from the bacteria contamination. That drilling processes having problems and contamination, that's increasing the H2S. So this is one of another problems. Tar. During also drilling, sometimes of the wells, we are finding tars like in breaking or holding from the processes of drilling. So another challenge, another problems we are facing, we can address the biotechnology to solve these problems. And also, as I highlighted, high H2S. And you know what is H2S problems can concern during the process of drilling and health problems. So not only just health problems, also even reducing the values of the oil price and having extra problems for the pipelines, which causing a corrosion and a problem. So all these challenges, we have it in the field. We need to involve the biotechnology to find a solution. So from there, what we did, we put our objective to set that challenge and problems. First, we try to develop innovation solution for the upstream application. Also, develop a novel environmental friendly components with the commercial value. So when we are going to the market, we have really competitive value. In addition to that, we have to develop an effective, cost-effective solution to determine the productive zone, as I say, the spotlights or sweet spotlights. In addition to that, the bioprocessing in situ. When I'm saying in situ, that means downhole. That means we try to sort the problems in the spot, under the grounds, instead of bring it up and treat it. So This is also one of the things which is giving us a powerful solution. In addition to that, to understand the formation, when we say the formation is the level of the, or the, what do you call it, the layers of the grounds or the earth. So we try to, when during the drilling, that formation, we don't want it to be healing down, so we need to be sure that no, we are not causing any damages in that formation by applying some of the solution from our biotechnologies. So with this objective, what we did, we put our program. And that's biotechnology programs relying on 3 domains. The first domain is the oil field chemical production, where we can produce a chemical, oil field chemical, they call it as a chemical. You can see it, biopolymers, biocatalysts. Now, which is the hot subject about the hydrogen, carbon capturing, which is the high subject, or what they call it, global subject, everybody running behind it. We can generate a hydrogen, we can storage hydrogen, and also we can capture the carbon either in the ground or under the ground. And this is one of the tools that we have it, and powerful of that organism that we can use it for us. In addition to that, the bioprocesses, that the heavy crudes upgrading, that means what upgrading? Transferring the heavy crudes from the heavy to a lighter. As you know, as much the crude is light, as the value and the price is high. So by that conversion, we can have a great price for our product. So that means with this solution, we can have it. In addition to that, as I highlighted about the desulfurization, and we say, when I say sour control, don't go for the Chinese food or for the sour meal, but it is like a sour, which is the high H2S. In addition to that, the in situ production, where we try to identify the well and exploring the well from the surface, and I'm going to talk about it in more details in the coming slides, where we can identify the size of the field, the location of the spot we're going to drill on it, and etc. So from here, I'm going to talk a little bit more in details about each of these. As I highlighted, the high temperature enzyme fracturing fluids. In the oil industry, the gel, they are using it, and they do it, as I highlighted, to fit that fracture, and they do it. But in the area which is high temperature, there's a limitation. They don't have that gel can precise that high temperature. But we managed to do that. Also, try to customize the biocatalyst and the biosurfactant to, as a biosurfactant to remove some of the oil. Sometimes when we have the oil spill in the ocean, we can use the surfactant or biosurfactant, as you can see it, to drag and control that oil. In addition to that, even for the bioengineering, for the environmental impact, also as a continuation about that oil spill, especially for the wastewater that's having oily water, we can treat it by using a great product that can make a good separation, as you can see it's in the scrub. Moving to the second application, which is the bioprocesses. Over here, in situ reduction of the high H2S, we can do that. And we can also, utilizing our special strain of bacteria to break down the long chain of the oil as a hydrocarbon to a small chain. And as soon as we are modifying this long chain to a small chain that we are converting the heavy crudes to a lighter crudes, where we put it as a good value for us. In addition to that, we have the enhanced oil production. We're trying to increase the oil production by, sometimes, as we can see, we do have like a fluids disturbing. We can minimize that with some of the treatment and practice with the biotechnology production. The third element, or third section that, as I highlighted earlier in the programs, is the in-situ production, sand. The same problems that I highlighted with the water production, some of the area of some of the zone, we have a sand production, and especially in Saudi Arabia, we have an area that is really controlling the sand during the drilling is really one of the problems. And that's costing the company a hell of money. So when you are drilling and that sand is production and stucking the pit, you need to remove it. And that's another, what do you call it, lose of money. You need to what do you call it, to manage it. So managing the sand production is really one of the challenges that you have it, and we managed to address this. In the coming slides, you're going to see it. One of the other things about the tracing of the, what do you call it, sweet spot, usually in the drilling, or what do you call it, and in the production section, to enhance it, they do like fractures. As you can see it over here, that fractures, they need to identify this fracture and they hit it by guns and sometimes by every ER. And that's hitting guns, they do it randomly, okay? Sometimes 10, 20 guns doesn't work. Maybe after 20 guns, maybe work. But tracing that with a biotracer, that will give you where you shoot your gun exactly for that spot. So in this case, you're going to limit the processes or limit the guns to do the fracturing in a certain places. That means cutting the cost. Another, what do you call it? Another stories about the, sometimes with the time, sometimes the oil itself is being immigrated from area to another area, either for cracking or with the timing is the zoning changing, that's oil being immigrate. So sometimes when we try to drill based on data, we could not find that oil. But what we are doing, we try to trace it, and where it's going to be immigrated, this is where we can using a biotracer to trace where that oil being immigrated from that zone to other zone. So in this case, we are hitting the right zone for the drilling processes for us. So from here, we put our as you can see, some of our project also addressing these challenges. And in the coming slides, I'm going to talk about more details about this project. So to give it some of a flavor and more details to see where we are doing or what we are doing in biotechnology program. The first project is development of a biomarkers for the production of the, or for the hydrocarbon exploration. As I highlighted in the previous slides about the GPT journal, where we try to exploring the well from the ground. What we're trying to do is to get sample from the surface to identify the sweet spot from the surface, because the technique we are using nowadays is using the satellite. The satellite will making a screening to a certain area which has a potential for oil over there. Then from that satellite, they say, okay, this area will have an oil or potential, let's say, potential oil to be drilled to find it. But with this technology involving a bio, we can have it and we can select some of this area has a potential, either for the sand formation or the carbonate, as we can see it. In addition to that, we can have identifying the size of that field, maybe small field or bigger field. With the size of the field, we can also utilizing this. So this technology this video going to show it to you more details about this technology. I will leave you with this.
Biodentify offers a revolutionary new technology that predicts the location of sweet spots with DNA from a 1-foot deep soil sample with an accuracy of 70% before drilling. It saves costs and environment and increases development speed of a shale play. If you think this sounds too good to be true, this is how it works. Every sweet spot produces microbubbles, moving upward vertically through microcracks, reaching the surface within several years. The amount of seepage is too small to measure, but it does influence the composition of millions of microorganisms in the ground. Some of these bacteria vanish because of these hydrocarbon molecules, while others flourish. By extracting the DNA from a surface soil sample, we obtain a DNA fingerprint that consists of all the different species that are present.
Right here I have a well plate which contains samples which were taken about 1 mile apart. So together this plate represents an area of approximately 10 by 10 miles. We have developed specific workflows that are extracting bacterial DNA, producing tagged 16S ribosomal DNA sequences. So this is a next generation sequencer which enables us to generate enormous amounts of DNA sequences of all bacterial species present in the soil samples.
After determining all the species and all the samples on the grid, we have a huge amount of data. Our patented triple-loop supercomputing software models most relevant biomarkers that are present or absent about the sweet spots. By comparing these results with information present in our biomarker database, we can predict whether there is a sweet spot or not. So the deliverable of this patented workflow is a clear and detailed map where the sweet spots can be found.
Our predictions have proven to be more than 70% accurate. And when drilling enhances the extent of field-specific information, the accuracy of the sweet spot prediction will increase even further. Biodentify is a joint venture of TNO and GOA. Their combined strengths resulted in this unique method of hydrocarbon sweet spot identification.
These are exciting times. Several years ago, this method wouldn't simply be possible. But thanks to recent DNA developments and progress in supercomputing, we push the limits of our capabilities forward.
Okay, I hope you enjoy it. So, the technology based on what? We're getting the soil sample, extracting the DNA from it, doing the DNA sequencing, and using the, AI technology. And from that data we generated from AI, we can identify the sweet spot. We can define the zone where is the oil there or not, either from the surface. So we are doing this, and we are working it, and it's going to be what they call it, a breakthrough technology, which is going to change a lot of things, using a satellite, which is really very cost processes and cost in doing it, to a simple processes and cost effective. So moving from here to another project, which is the sand controlling. As I highlighted, we have in this business a sand, especially in the sand formation. That sand is really, during the our operation, having problems. That sand also coming from the down to the surface, and especially at the wellhead. And at the wellhead of this well, it's when sand accumulated, and especially on the certain valve and check valve, and very process is going to be making a jump. In addition to that, when it's going to be moving from the surface to the pipeline, is going to be having erosion, corrosion, and a lot of problems, and especially when it's moving to the tankers. And all these problems created by the sand. So what we're trying to do, we try to put and make a consolidate the sand in the reservoir, so to eliminate it from going to the surface. So in this case, we stop the sand movement from the downhole to the surface. So what's available in the market is a chemical that can joining and gluing the sand as a resin and non-particles polymers, and it is really good and very, very strong. But sometimes in oil and gas industry, some of these zones, we need to go back to it and drill on it for a certain subject or certain business. But with this technology or with this treatment, it became like a glue. We cannot go back to it. But in our process or our operation, we need sometimes, and mostly we need to go for a certain job to do back. So that has a limitation. So what we're trying to do is try to develop environmental friendly and reversible, and this is, we can go back again, drill in it, chemical sand control method. So what we did, we tried to get a calcium carbonate between the lowest grand sound resolution. What we did in our lab, as you can see this, the chemistry, and by developing a novel chemical component based on a bacterial strain's enzymatic process, and this is a patented product, we managed to build almost a solid and combination banding the sand particles together and make it really solid. And in our experimental showing that, what we did, we bring the loose sand, we treat it with that component, we put it in a different temperature, room temperature, and high temperature. We reached to until 170 degrees centigrade, and still we managed to have a solid sand. And as you can see it from the SEM, where we are, the first columns of pictures or photos showing with the control without any addition of our novel component. We can see the space, but as we put our component, we can see a build of that calcium on that space. So that means we managed to fill that space and we make it as a console and solid particle. So we managed to do it. And as soon as we need to go back and clear it, so we go back to it, we can, with the acid treatment, we can go back again. So retrievable. So in this case, we managed to go and apply it in the field, hold the sand, and as the operation, they need to go back and drill on that. We say, okay, go back and do it. So we managed to do that. Another project, which is one of the project or one of the problems in the drilling, and as soon as the challenge the problems is, as soon as the drilling process is happening and utilizing there is a microbial contamination on it, and utilizing the water which is not being sterilized and not being treated with the biocide. When we say biocide, this is the terminology like antibiotic. When you are sick, as a human being, you are taking the tablets, and especially now in cold, we are taking the tablets as an antibiotic, but in the oil and gas industry, we call it a biocide to kill the bacteria. So in this case, what we are doing, we have the drilling process or drilling materials with the starch is as soon as we are mixing it with the water, and that water is being contaminated with the bacteria, we having problems. And that's a problem causing degrading the drilling fluid itself. So the drilling fluid will not going to doing the business as needed. So in this case, we'll lose the viscosity. Also, in addition to that, it's going to having H2S increase, because that kind of a bacteria increasing the H2S. Also, as I say, degradable when you're going to the reservoir, degrading the carbon. What is the monitoring program they have it nowadays, or in the place? They call it ATB. They get the sample from the mud, they get it to the lab, they do a serial dilution, master bubble number testing, and to test, do we have a bacteria or not? Do that bacteria available or not? And that takes from 7 to 28 days, which is an oil and gas, and it is really cost effective because the drilling mud engineer, he need a quick answer. We have a contamination with the bacteria or not? So what we did, we tried to develop a methodology on site to be sure that we are testing the drilling mud on the site and get the answer quickly. What we did, we're using a technology, they call it ATP, adenosine triphosphate. This is the component of energy of any human being. What we're trying to do is to monitor that. And the technology is simple, can be done where we are trying to do it on the site, simple kits to the site, where that ATP, as you can see it, as being reacted, will be knowing the quantity of the bacteria and how much does we have it. So from there, we did several several testing in the sites. We collected several samples from the drilling, from the water, from the drilling mud, and we manage and we compare it with the current testing with its MPN, and we see it is really matching. So in this case, we're proving that ATP, we can use it in the site. Within a few minutes, we can get the answer instead of waiting until 28 days. So we start implementing this and going to be deployed. So from this project, we can see what this potential application we can use it as a biotechnology. And the exploration and progressing, as I highlighted, and the drilling and completion, where we have a lot to do, in the production and recovery of the oil. In addition to that, we can see a lot of application of the biotechnology in oil and gas industry. Also, in addition to that, and for the production and processing, and sustainable environmentally, where we can have a solution for that. So, from here, I can conclude that we are developing with this biotechnology, developing a technology based on the 4th Industrial Revolution, cost-effective tools, and creating a novel tools for environmental friendly product and environmental friendly to be used for our formation. With that, I'm concluding, and thank you.
Thank you, Dr. Abdul Mohsen, for the wonderful presentation. And now, we're honored to have Ms. Harmeen Mehta, a global technology strategist and innovator. She will be guiding us through from learners to innovators, highlighting the role of undergraduates in driving intelligent systems forward. Please join me in welcoming her with a warm round of applause.
Everyone. Good morning. All right, that's a little better. So today, one of the things I thought we'll cover is actually looking at what the conversation we had yesterday and the conversation that I've been having with the team here at Jasser on how to take a lot of the things that you guys are devoting yourself to and the research you're doing, and how you can help put it to a little bit more practical use. So let's see how it goes. I fundamentally believe that, okay, the clicker is a little shy. So how many of you believe this, that somebody in this room is going to write history? Very few of you. Well, thank God, Richard, you raised your hand, otherwise we should have been worried for Neo. First thing is believe in yourself. If you're dedicating yourself to any kind of research, why are you doing that research? You're researching something that has not been solved. And there are many problems to be solved. And if you think, I'm just starting out in my life, how do I know whether I'm going to really reinvent something or not? That's what a lot of people did. Bill Gates and Paul Allen, they started Microsoft when Bill Gates was still at uni. He dropped out of Harvard. Mark Zuckerberg, Facebook was a social networking thing that was created for the students inside while he was at Harvard as well. Another example, Elon Musk actually created Zip2, and the entire idea of doing it was while he was studying physics and business. And the story goes on and on. If you go and look, Michael Dell, actually for a few years, he started a couple of businesses while he was studying. One of the most famous companies of the world, Google, Sergey and Larry, it was actually a research project for them. And that's what gave birth to Google. So a lot has been born. The next one, Snapchat. Again, 3 friends collaborating while they were studying. Yahoo, exactly the same story. So some of the best, topmost companies in the world have been created by students while they were studying. And at least 3 out of these have come out of research projects. So, but the most important thing is you having the belief in yourself that you can do it. See, the amazing thing is that if you really look around, if you believe in yourself, you will put a very different effort into what is, it's a lot of conviction that needs to go into research. You're on a path which is not traveled before. You're researching something that hasn't been found yet. And if you don't have the conviction that there is an answer to that problem, then you will not find the solution to the problem. I mean, yesterday, just sitting in the audience, hearing about, so many different things that you guys are doing, hearing Richard talk about NEOM and, crazy concepts. Well, once you have a belief, then you will work towards making that happen. That's how inventions happen. That's how innovation happens. So it all starts with, if nothing else, if one of you can believe today that you will be a part of something that will get somebody standing here in a few years will have your picture on that slide, then it justifies me getting on a flight and coming here. If you were really to see, the world has so many problems that we haven't solved yet. We haven't found the solution to so many things. And so many of these were big problems before, but they've become gigantic problems now. I'm going to highlight a few of these. Just human productivity. The pace in which the world is moving, the pace at which we are going, the pace at which technology is actually needing for businesses, industries to evolve, with the rising needs of, just the talk we heard before, by getting more accurate, more precise on our drilling, as well as on how to really extract the most out of the oil that we are, that's so fundamental to this country. Just getting that little bit better, a little bit increase in that productivity, a little less wastage, itself is going to give us years of longevity on the same product. Imagine if we could take that piece and translate into everything. Productivity out of our daily lives, productivity out of you as students, productivity out of the university, productivity out of the country. How much more we'll be able to do? I just thought I'd put down a few examples. AI could actually contribute up to 16 trillion to the global economy. Not my figures. All my sources are listed there. But it is something, we are talking about the GDP of the planet could go up by 14 to 15%. That is the potential. At the same time, just for us to cope with the new world of technology, for industries, for companies to be able to do more, produce more, innovate faster, we're going to need a 70% increase in our own productivity. The Earth is going to have 9.7 billion people. Feeding those 9.7 billion people, transporting them from one place to another. What it means for everything from roads to transportation to the fuel that's going to be needed for that, to the impact on the same, there's only part of Earth we have cultivated. We've either used it for industries or for living or for agriculture. So there is only so much more land to find. We found all the land that exists on planet Earth. It's all going to be a story of productivity. Manufacturing. There is a potential of us creating trillions of dollars of value by just increasing the efficiency of what we produce and reducing waste. At the same point, just repetitive tasks. How many of us do repetitive tasks? In every organization, there is so much of repetition that you do. Just automating that as well is going to really cause an increase in productivity. But that's one. That's one of the problems. Climate. The impact that the climate is having is unprecedented. One of the pieces, I don't know if you guys have read this, but 23, if we can create all that value, AI creating 16 billion, well, 23 billion is going to get eroded just because of the impact of climate change. Look at what's happened in LA. It's taken us days and weeks to put out the fires. Millions of people have lost their homes. All that needs to be rebuilt. The environment is getting worse with every disaster. Every tsunami that comes in erodes billions away. That's just taking productive money and putting after an impact. And what's caused that impact? It's all of us. It's everything we have done. Everything we are doing is contributing into making the environment worse. It wasn't somebody else's fault. It's all of us. We all have a role to play in it. Every time you let the tap open for a few seconds longer, you let the food that we waste, the materials that we use that we don't recycle, that we could have recycled, each and every single part plays a role. Why? Because it is 8 billion of us doing that small little piece. You multiply it by 8 billion times, and you can see the impact. And then you multiply it by every day that we live, thousands of days, you can see the impact. But we also have the opportunity to do something about it. Just by accelerating the solutions and whatever solutions we're working on, just by accelerating them, could actually reduce the impact and also increase the positivity that will come out of it, and could have a massive difference on slowing down the climate degeneration and accelerating the climate regeneration. Methane and carbon emissions alone, optimizing those by just 20% will have one of the biggest impacts on the climate. So anything we do, anything that you can do, and anything that you are working on that can have an iota of impact on this will get multiplied many, many folds. Let's talk about healthcare, drug discovery. We've all gone through a pandemic. And we've seen the impact that, in fact, what was that? That was a virus that caused some respiratory problems, that caused a bit of a flu and a cold. And there was one time when out of the 7.5, 8 billion people that exist on planet Earth, 50% of us were actually under home curfew at one point in time. If somebody had told you even 10 years ago that there is going to be a time where 50% of humanity is not going to leave its house, who would have believed it? I wouldn't have. It's a great topic for a Hollywood movie. It's a very difficult topic when you are living through it. But that also told us how many billions was spent by the pharma industry actually trying to accelerate the drug, because normally it takes us years to manufacture, test, and mass produce any drug. And it costs billions. But with quantum computing, we can really change that. Chronic diseases, 70% of the deaths are caused by chronic diseases, and 400 million people at any point in time are said to suffer through very rare diseases. The impact of biomedicine to be able to just change the composition of drugs by understanding and sitting inside your body and understanding that composition could actually create an impact where we could have personalized medicine. That is the power of quantum computing as well. It could really accelerate drug discovery. In fact, it could accelerate today prediction of even the topic before we were talking about climate. We have never got, we don't, even today when we have so much advanced technology, we've got companies like Google, the weather company, IBM, everybody focused on identifying the weather. We could not predict that this is what was going to happen in LA. So there is a lot more about being able to do this in real time, in very near real time, and being able, the impact is saving lives. The impact is also making this earth livable for another few hundred years. Because we are very fast accelerating an impact that actually we might not live beyond 100, it might not be livable beyond 100 years or so. And the biggest problem that I feel that exists is each one of us thinks it's somebody else's job to solve it. And each one of us thinks we do not think enough about the impact that I am having, the impact that you are having, and the impact that you could have. Other pieces, what else could be done? Well, space exploration. If we can't stop destroying planet Earth, well, we better find other planets to live on. And the reality is, if you look at, as humans, there is one ingredient, the exploration is something is in every single human being's DNA. That's how we discovered, Columbus discovered America. He didn't know where he was going. He just knew there's something out there, I've just got to go and find it. That's how the Wright brothers actually invented the aeroplane and invented flying. They just knew there's got to be a mechanism. If birds can do it, we can find a mechanism to make humans do it as well. And I know there are lots of, now there is a lot of interest, there's a lot of focus in really finding the right solutions for this. And NASA said, well, in 2040, 1 million of us could be living and working from Mars or Moon. I'm not sure how much of that is going to happen, but our job is to really work towards it. Yesterday we were talking about, a lot about the power of different materials and minerals and discovering that. Well, imagine extracting that from asteroids and our ability to be able to do that. That is quadrillions of dollars of value that could be created. And then, of course, there are millions and millions of planets. Well, somewhere else, there's bound to be the right environment, or where you could create the right environment. And you don't know that till you get there. I mean, a few hundred years ago, for people to think that you could actually sit on a Concorde, fly from London and reach New York, and you reach New York before you've started, the time is earlier than you started from London. Well, it was possible Today we fly around the world, 16 hours, you're in the opposite side of the world. It is possible. The same exploration would take years, many years back. So today it might take us years to find a way of getting to Mars, but once we perfect it, it'll be no different than any other flight. And I believe that that is probably the likelihood that we will see that kind of world while we are alive, definitely while you are alive, very high possibility. So there is a lot to be discovered, there's a lot to be done, there's a lot to be solved, there's a lot that is still possible. And in fact, it is more possible today because all of you have the power of the latest in technology, which actually people in the yesteryears when they were making these discoveries don't. But what is the ingredient that you need? Well, the biggest one is curiosity. How curious are you? When you see something, do you just see it? Or are you curious what's behind it? When I talk about, living and working from Moon or Mars, what's the first thought that came into your mind? Crazy? Or what would life look like? What would I do? How would I go there? If you don't have curiosity, then everything you do, whether it's a research or it's studying something, it is a mechanical motion. If you have curiosity, it becomes an intellectual motion. If you have curiosity, it leads you, it becomes a quest for an answer. It becomes a quest to understand. It touches your heart, it touches your mind, it touches your soul. So what do you want? You're dedicating years of your life to learning. How much is it touching your soul? How much is it really touching your being, where it's making you really think, believe, and want to do more? That kind of researcher is the one whose photograph ends up on a presentation like this. Another ingredient is the power of teamwork. And teamwork, I don't just mean, just working, just being able to talk and collaborate with each other. I mean real teamwork. Yesterday, when I was walking around and seeing a lot of the papers that were on display, I couldn't help but think that somebody who is working so diligently on discovering the power of different materials and different kind of fibers and what we could create with it. And then somebody else was actually working on Biotech and trying to find out that how can I produce a material or find a material that could actually have a similar density to a bone but have the flexibility of a balloon so it could take whatever shape is needed to take. Well, imagine the power of 2, 3 of those just coming together and working together. Then you solve something. And it's your curiosity that would lead you to go and see who else, what somebody else is working on and how you could really collaborate with them. I've heard so many of the professors that I've been meeting over these last couple of days talk about how they're collaborating all around the world. Different universities, different people they've never met, but they're collaborating with them because they have an expertise in a particular area that really fuels their research. The tiny little ant, and then forget about the ant, look at the even tinier and thinner leg. An ant can carry more than 10 times its own weight. Humans struggle to carry 1 time in their own weight. And a group of ants can carry more than 100 times their weight. 100 times on those tiny little legs. the power of being able to work with each other, work with people of very different intellectual strength, very different fields of curiosity, but bringing that together to create a solution, it is absolutely immense. But the one thing I would say is that a lot of this has to be towards creating something, towards building something, not towards just doing it. And you need a lot of persistence. You need, in fact, this is your country's saying that the world learns from. Your strength, the strength of your Tuwek Mountain, the strength of each and every one of you, how do you harness that? That is the perseverance you need. If you haven't solved it, it's just because you haven't found the thing that solves the problem. But you need to keep working at it. And thinking differently as well. But all of this starts with only one thing, is the ability to dream, is the ability to believe in yourself, and the ability to say, yes, this is the best gift that I have is I have a problem that is not solved. That's what I'm going to dedicate myself to. And that's the passion that you need. So, what are you going to invent? I'm going to leave you with that. Thank you very much.
For your incredible presentation. Now we'd like to share the afternoon offerings with you, starting with a workshop on scientific writing for research publications by Dr. Mohammed Tahir at 12 p.m.
And don't forget the oral sessions at room 105 from 1 p.m. to 3 p.m.
Then we have a poster designing session by Dr. Qasim Darmoush at 2 p.m.
And creating with 3D printing with Mr. Osama Shimmari and with Mr. Sadiq al-Badr.
And don't forget to check out our exhibition and immersive pavilion in Building 54 from 12 to 4 p.m. today.
And all the amazing social activities we have prepared at Building 19.
JISR really has it all, so make sure you don't miss out.
And now, to welcome our next speaker, Dr. Atif al-Zahrani, the Director of Interdisciplinary Research Center for Sustainable Energy Systems at KFUPM. With a career dedicated to pushing the boundaries of renewable energy, Dr. Atif is here to take us beyond lithium-ion batteries, exploring the next generation of sustainable energy solutions that could redefine our future. Please join me in welcoming him with a very warm round of applause.
Assalamu alaikum wa rahmatullahi wa barakatuh. Alhamdulillah, salatu wassalam ala rasulullah. First of all, I would like to thank all of you for being here. I would like also to thank the organizers. From the students to the students. This is the first of a kind conference, and for that I really applaud you. Thank you very much. And today's presentation is about beyond lithium-ion batteries. Lithium-ion batteries is now ubiquitous, so basically it's everywhere. And I want to just address the point, okay, what is after the lithium-ion battery? But before we start, I want to address one point or ask one question is why do we need even lithium-ion battery? And from there, we can understand why lithium-ion battery is important and what are the challenges with the lithium-ion batteries and how we can resolve these challenges by innovative technologies that is beyond lithium-ion battery. So first of all, to put things in perspective, if you look at the electricity generation that we have here globally, it is mostly dominated by the fossil fuel. So I'm talking about 80% or more than 80% is coming from fossil fuel. 2009, 80.3. 2019, 10 years later, is 80.2. So still we are relying on fossil fuel. And this percentage hasn't budged because of two main reasons. The first one, now we have more people who have more access to electricity. Second is that the fossil fuel are good in terms of being a reliable source of energy. It's not good for environment, but it is good as a source of energy, a reliable energy. And we have established technologies to convert that chemical fuel of diesel or, for example, gas or oil into electricity. So it's well-established technologies. So in Saudi Arabia, for example, this is not including the recent ambitious goals and development and deployment of renewable energy. We are mainly relying on oil and gas. But we know that in Saudi Arabia by 2030, we need to achieve 50% renewable and 50% gas, which is a very ambitious. We are talking about 20 gigawatts of renewable energy every year. Humongous amount of renewable energy, very ambitious and to be uploaded for. So this is the current scheme. So I cannot stress enough that the fossil fuel is good of being a reliable source of energy, but we know that it has its own consequences, okay? And one of the consequences is the global CO2 available in the atmosphere. This is the cumulative amount of CO2 in the atmosphere. We are now into uncharted territory. So we are talking about 37.5 gigawatts of CO2 in the atmosphere. There have been a few blips in terms of the trend, but the trend is moving upward, okay? So for example, during the COVID-19, there was some optimism that we have now finally reduced the CO2, but it's because of the lockdown. So this is where we have now the CO2, and it has a consequence in the global warming. As you can see in this graph here, so the graph here is showing that compared to the pre-industrialized era, we are now plus 1.3 degrees. And I mention 1.3 because if you know about this climate actions, we have one famous agreement. It's called the Paris Agreement, and the Paris Agreement that we should limit it to 1.5 degrees compared to the pre-industrialized era. As a matter of fact, now we are talking about 1.3 degrees. So how many years left before we reach to this 1.5? We introduced the concept of carbon budget, okay? And from here you can see that if we are gonna hit the 1.5, assuming that we are continuing with the normal practices, this is the amount of CO2 left. Again, this is approximation to some extent. So we are talking about less than 10 years, by the way, we reach 1.5 degrees. 1.7 degrees, this is the amount. We are talking about tens of years, maybe less than, or 10 to 20 years, and 2 degrees, we're talking about some tens of years. So it is a little bit alarming, but what I'm presenting here is not something just to make you worry. It's not something just to make you panic. It's in fact a call for action. So what kind of actions that we can take as a society in order to address this issue? One of the main and most important action that we can do is to shift to renewable. Why? Because as per estimation from the ARENA, which is the International Renewable Energy Agency, renewable energy and electrification alone can deliver 75% of energy-related CO2 emission reduction needed to meet the climate targets. So renewables are good in terms of reducing the CO2. So you might be wondering, okay, let's shift to renewable. And in fact, the 2030 goals, 50% renewable, 50% gas, why not 100% renewable? So we need to shift to renewable, but there's some mainly technical challenge, of course, financial issue, but technical challenge is one of the main thing. This is a graph from the ERCOT, which is one of the electricity companies in US. And the y-axis, you can see the months, January, February, March, April, and the x-axis here is the number of days. We have three colors. We have blue, red, and black. The black is basically the load, how much we need, the power that we actually use in that area. And the red one here is the solar generation from the PV, and the wind generation is in blue. What do we notice here? We notice a common phenomena for renewable is called the intermittency, okay? Now we are living in our homes. If you ask yourself how many times and for how long electricity was out, you might be thinking maybe twice, 3 times. So this is what we call reliability and resilience of the electricity that goes to you, to your home for your own usage. But as you can see from the renewable here is fluctuating, which is by nature. The sun is out, we have electricity, the sun is down, we don't. And if the wind is blowing, we have energy or power, and if energy is down, we don't. So this is the problem with the renewable. So we have to resolve this problem, okay, just to make it more stable in order to meet the demand. Sometimes we have more production of renewable compared to what we need, sometimes lower. So how can we really make sure that renewable is, again, reliable and resilient? We have technologies, but the most important technology that we need is energy storage. Can we store that excess energy and use it whenever we want? And just to make sure that we have a resilient and reliable electricity, this is basically the concept of energy storage. So without energy storage, renewable energy cannot realize its full potential. And this brings me to the topic of energy storage and lithium-ion batteries specifically, because it's one of the most fastly deployed technology when it comes to the energy storage. So, but this is only one area where we use lithium-ion battery. But there are many areas we can lithium-ion batteries using electronics, okay? If you try to close your eyes and imagine, okay, without batteries, how can you live your day? It will be hard. It will be difficult. Now you are, for example, holding phones. I'm using this microphone, of course, with the batteries. I'm using so many things, laptops with batteries, so many things with batteries, okay? And this is for the smaller scale. We have, of course, the EV, electric vehicle, with the medium stay kilowatt hour range, and we have the renewable, as I mentioned, in the megawatt hour range. So the lithium-ion battery is ubiquitous. So basically, it's everywhere. We need it. We will continue to need it. And we even need it at a higher, deployed even at a higher pace compared to the previously designed. And that's why it created some shortages in terms of elements, critical minerals, and so on, okay? So this is a statement. I'm not sure if you agree or not, but you can see from this statement that the lithium-ion batteries have brought the greatest benefit to the humanity, enabling the development of laptops, mobile phones, electric vehicles, storage of energy related from solar and wind power. Do you agree with this statement or not? Okay, if you agree, then congratulations. You should be part of the Nobel Laureate Judging Committee, because this is part of the statement from the Nobel Laureate Prize. That's why now 2019, it has been awarded to 3 scientists. We have John Goodenough, and we have the Stanley Whittingham, and we have the Akira Yoshino. So these 3 scientists basically helped in developing the lithium-ion battery the way that we know it to do. But it was a difficult decision because many have contributed one way or another to the development of the lithium-ion batteries. And they are not working in the same lab, by the way. They are different people from different labs, but each one of them developed something that contributed to the lithium-ion battery that we have now. For example, in the early days, 70s, Stanley Whittingham developed what we call using a certain chemistries, molybdenum disulfide with the lithium itself. It was dangerous because, as you can see from the newspaper here, it's called Moving on Moly, and you see the picture here is we have a battery with like, for example, it's like a bomb, which is, in fact, to be honest, when you talk about the energy is like maybe a smaller bomb, but this was dangerous, okay? In the 80s, early 80s, John Goodenough, he developed another chemistry, which is basically on oxide materials, raising the voltage, having more energy, but still have some problems, especially on the other side of the battery. And here comes the Akira Yoshino, he developed some chemistry again. The way that we know batteries now is relying on that chemistry. So each one of them, they contributed to some degree or another to the development of the lithium-ion battery. So the people appreciate how lithium-ion battery is changing their lives, and that's why it has been awarded in 2019 for that category of the chemistry. Okay, but the batteries themselves, of course, they have some challenges, okay? So I'm trying to list here some of the challenges, and when I say the challenges, I don't mean that we don't use it because we are using batteries. But I mean challenges that these are points that we can basically address to have even better batteries. So one of it is the cost. The cost now is $130 per kilowatt hour, let's say, per cell. Now we need to drive it to even lower cost. Lower cost, of course, is more favorable. And we have the energy density, how much energy is contained within the battery. We have the power density, how fast we can utilize the battery. So it's two different things, the energy and the power. But we need to improve them further. And we have the safety. Of course, safety is one of the main issues for the batteries. And we have what we call the first life to address the sustainability. So if you are done with your battery, can you use the battery again? So when we say that, for example, your electric vehicle, which is inshallah in the near future, it will be very common to see electric vehicle. So let's say that instead of 100 kilometers, now it's just 80 kilometers. So you might be thinking, okay, this is khalas, I'm done. We need to buy another battery. But that battery is still good, so can we use it in another application? Temperature, for example, we have very high temperature here, but also we have very cold temperatures in some other parts of the world. And if we have a battery that can both survive low temperature, extreme weather condition, that would be even good. And also the predictability, when the battery will fail, when it will reach to a certain amount or a milestone. And finally is the sustainability or recyclability of the battery. We are deploying like there is no tomorrow when it comes to the battery and renewable energy technologies. So the question is that after we end up with this technology, how can we recycle it? These are all points to consider when it comes to asking the question is, what is beyond lithium-ion battery? And for this topic, I'm just gonna point out to 3 technologies in brief for what is beyond the lithium-ion battery, addressing some of these basically points of improvement. So first of all, let me talk about the cost. And before I talk about the technology, let me just give you one statistic or two about the lithium-ion battery. First of all, I want to explain to you a little bit the science behind lithium-ion battery. It's like something like, for example, you have a sandwich, and the sandwich, we have 2 sides of the bread. And these 2 sides of the bread, we have one electrode on one side, we call it the positive electrode, or we call it, for example, the cathode, and we have one side of another electrode, it's a negative electrode, or we call it the anode, and between them, we have a separator just to avoid basically having touching each other and short-circuiting, and we have the liquid electrolyte. basically where we have the lithium ion going from one side to another. Might be boring for non-chemists or electrochemists, but basically we have the lithium ion going from one side to the other side during the charging and discharging. So if I ask you, and if you can get something out of this presentation, the components of lithium-ion battery, you can say, you know, we have positive electrode, we have negative, we have electrolyte, and we have a separator. And this is basically the main thing. So the electrolyte is something that is liquidy, and the lithium ion will move again from one side to another. It will be reacting with the positive. It will react also with the negative electrolyte. This is a lithium ion battery. And before addressing the cost again, I want to point out that the lithium ion battery is undergoing a with a very fast pace of development. This is, I'm talking about 30 years or something ago. This is from movies from 1980s, okay? And this one, he's using a mobile phone, supposedly mobile phone. And from here, this is 1,650 pounds is from Vodafone, and the transportation is basically, it's a lead acid battery. And the weight is 11 pounds, so 5-point-something kilos. Imagine that you have a phone now weighing 5.5 kilo, okay? It's, now we don't even, you know, notice whether we have a phone in our pocket or not. Sometimes we forget about it because it does not weigh anything. And look at the other movie, for example, is of course $4,000. And here is a nickel cadmium battery, 10-hour charge, 30 minutes in action. So you have to charge it for 10 hours in order to end up with the 30 minutes of utilization. And I'm not talking playing Angry Birds or whatever in that phone. I'm talking about just using the phone to call, just 30 minutes. Now, this is in the 80s. Now here, if I tell you, now we can use the phone doing sophisticated stuff, and we need to charge only for 1 hour maybe, or 30 minutes, and use it for 10 hours. So the development of lithium-ion battery has been a remarkable journey. The reason I'm saying this one, because it will lead me to the next slide, and in the next slide here you can see that the energy for the battery here has been increasing. Now we can use the batteries. I mean, you can see this is increasing. At the same time, the price of the lithium-ion battery has decreased with the years. So the x-axis is not something like pre-industrialized era. I'm talking about 1980 until now, 2000. This is an outdated, but the point is just not to give you the exact price, but the point to show you the trend, okay? In the 80, it was 8,000, something like around 8,000. Now we are talking about 100. This is within the span of, let's say, 40 years, 30-something years. We have now achieved a remarkable reduction of the cost. But still, scientists are greedy. They want to decrease it even further. And for that, we have very promising technology, and that technology is called not the lithium-ion battery, it is sodium-ion battery, relying on the sodium. I'm going to present just one slide. I don't want to bore you. But in this slide, you can see here, this is the sell price. This is basically up to here. This is a very recent publication, by the way, if you are interested. And this is in 2000, let's say 23 or 40. And this is the projected price. The price calculation and prediction is a little bit complicated, is not that straightforward, but include many things, okay? The learning curve and the materials and so on. And as you can see from this graph here, comparing two different technologies, lithium ion that rely on one chemistry, a very common chemistry, it's called lithium iron phosphate, and we have the sodium ion battery. And there are many graphs here, but let's talk about, for example, the forecasted lithium iron phosphate lithium ion battery and the forecasted the sodium ion battery. You can see at the beginning that we have, of course, the sodium ion battery will have a higher price because it requires some learning curve, scaling, and so on. But at some point, it will bypass, according to the calculation, the lithium iron phosphate. And the main reason behind that thing is the cost of the raw material itself. It's basically the mineral's floor. It's basically how the mineral can reduce its cost. The lithium iron phosphate has been there for so many years now. It will reach to some stagnant value, but the sodium ion is something emerging. So this is to address the cost perspective of the lithium-ion battery and how we can go to the next step when it comes to the reduction of the cost. Second, we have the energy density and the power density. In this graph here, we have the x-axis, the gravimetric energy density, and the y-axis, we have the volumetric, based on the volume, based on the mass. So if we start with the lead-acid battery, the pink colors here, what we call established technology that are already in the market. Lead acid, nickel cadmium, nickel metal hydride, and the lithium ion, which based on the graphite and the transition metal oxide as both electrodes for the lithium ion battery. But going forward, we can play with this chemistry. You can see that we have some emergent technologies, zinc air battery, lithium metal battery. The difference is that we don't use graphite, we use lithium. You know, this is the first thing that has been invented by the Stanley Whittingham. He used lithium, but we just forgot or basically abandoned lithium for one reason. It is very reactive, not safe. Now people or scientists, they are developing ways how to make it even safer, okay? And so we can use the lithium metal, and there are many interesting developments in that area. We have the zinc air, lithium sulfur. This is a personal favorite of mine. I'll mention why. And the lithium air battery and so on. If you focus on the lithium sulfur here just for a moment, you can do just a rough calculation or theoretical calculation here. This is the normal battery that we have almost in every mobile phones, more likely, that we have graphite on one side, and we have what we call nickel, cobalt, aluminum oxide on the other side. You can calculate what we call this capacity or the specific capacity. How much capacity or how much that kind of chemistry can hold electrons or lithium. So we call that capacity. So it's 279 milliamp hour per gram. And if you multiply by the theoretical voltage, we're talking about 606 watt hour per kg. This is basically the normal battery. Now, looking at the lithium sulfur battery, just replacing the graphite with the lithium, replacing the nickel, cobalt, aluminum oxide with the sulfur here, you can see from this graph that the capacity is 1670 milliamp hour per gram, which is the cathode side here. And if you multiply by the voltage, which is a narrower voltage compared to the previous battery, we're talking about 2660 watt hour per kg, which is really huge. Huh? And it's not only this, okay? The advantages are going beyond the energy density here. The lithium sulfur battery, that of course now we have limitation when it comes to the lithium-ion battery. The lithium sulfur, of course, can have higher energy density, but for me, I think one of the most advantages of the lithium sulfur battery is that we are relying on sulfur. Sulfur itself is a byproduct of the oil and gas industries. It's everywhere. We can get sulfur. You can get even sulfur soap. It's everywhere, okay? But if you look at the previous one, you have to worry about the nickel. We have to worry about the cobalt. Cobalt, 50% in the Republic of Congo or so. So we are talking about mining, ethical mining. We have to source material. It is geographically not distributed. It's located, concentrated. So there are many stretches when it comes to the supply chain. But the sulfur, it's almost everywhere. It's very dirt cheap to get the sulfur, okay? So this is when it comes to the one promising technology, which is the lithium sulfur battery to address the energy and the power. And the second thing that I want to mention also for another technology here of interest, this is I showed you before, the graph. And the energy and the power, we call them coupled. They are coupled together within this chemistry, okay? So within the chemistry of the lithium or within the chemistry of both the cathode and the anode, the positive and negative. Basically, it is reliant on the chemistry. So they are coupled together. You cannot basically differentiate, or you can play with the power without playing with the energy. They are coupled together. But another technology of interest, which is we are investing in also here at KFUPM, is what we call the redox flow battery, okay? It's a very interesting technology here. And the main advantage, or one of the main advantage, it has a lower energy density than the lithium-ion battery. But the thing is that we don't have a laser here, but the main thing here is that we have what we call tanks. So instead of having cathode and the anode as solids, we can have them as liquid, and we can store them in tanks. So this is the energy part, and the power part is basically the stack between them. So we can, and this is the main advantage, decouple the energy and the power, okay? So we can have as much energy as we want, and we can basically the power. So this is one of the remarkable technologies of interest now, and we are developing also this one in, inside the KFUPM as well. Finally, is we need to make the batteries even safer. Let's be honest, I'm talking as someone from background of batteries, I'm afraid of batteries, okay? I'm afraid of batteries. Because if you think about it and calculate the energy, not to terrify you, but if you take 3 batteries, I'm talking lithium-ion batteries, like what we find, let's say, in cars, the cylindrical shape. The 3 batteries, the energy contained within these 3 batteries is the same energy contained within a hand grenade. It is huge. The amount of energy is there. And maybe you have seen videos, you have seen maybe pictures of battery exploding, battery fire, because the safety is still a main concern when it comes to the batteries. And for that, we have to develop a technology. This is what scientists do, okay? So we need to make the batteries even safer, especially that with the temperature here in Saudi Arabia, as you increase the temperature, you will get, of course, maybe higher activity of the material, so you get higher performance, but it will die faster. And with the higher temperature, you will basically trigger the decomposition. You would trigger the failure within the battery. It can start from something, let's say, around 80 degrees or 70 degrees. And that's why we need always to manage the thermal environment of the battery itself. So how can we resolve this one? This is mainly coming, by the way, the main decomposition is coming from the liquidy stuff within the battery, as I said before, the liquid electrolyte. So can we go beyond the lithium or the liquid electrolyte? The answer is yes, we can go. It's not easy, but we can go. This is the normal battery. I told you, electrode from both sides, sandwiched, and we have liquid stuff inside. So we asked ourselves, I'm talking about scientists, that we asked ourselves, can we replace that liquid stuff? Maybe with a solid stuff instead of liquid. And that's why we have what we call now solid state battery. Solid state battery, where we don't have a drop of liquid inside. We don't have anything. It's just solid, ceramic, tough, strong, solid within the battery. You might be thinking, okay, that's really a good thing. So, okay, so no liquid, no flaming, nothing gases, whatever. Mainly, it's based on solid, so you have less risk, more safety, and so on. But again, there are many challenges. Ions, they like to move in liquid, easier to move in liquid than solid. Okay, this is basic chemistry, okay? So how to find basically another material or a material that can have a higher ionic conductivity. This is one of the main challenges, okay? So most of what we call solid state conductor, they have lower conductivity compared to the liquid electrolyte. So solid state electrolytes have lower conductivity mostly than liquid electrolyte. So we have to find a solid state conductor or electrolyte that has comparable or even maybe higher conductivity than the liquid electrolyte. But it's not only about having solid state that is maybe a higher conductivity, but there are many issues, and I can just spend even 3 lectures on each one of these issues. But here is a nice summary of some of the issues depending on the electrodes that we are targeting. If you talk about the negative electrode or the anode, we have basically interface problems. We don't have a stable solid electrolyte interface. We have a pressure issue. When it comes to the conductor or the separated solid state, we have, of course, the charge transfer resistance. We have other types of interfacial problems. And the cathode, here we have cathode interfaces between solids. And there, the liquid can go anywhere and react anywhere. Here we talk about the solid, so it is less immovable, and it cannot basically move within the structure itself. So there are many challenges, but this is basically what the scientists would like to hear, that there are some challenges, so we try to resolve it, and this is one of the things also we are focusing here at KFUPM. I hope that this presentation gives you a glimpse of why we need energy storage, lithium-ion batteries, some challenges of lithium-ion batteries, and some promising technologies to look for in the coming years for energy storage. And with that, I really thank you for your attention, and I'll be happy to answer any question. By the way, I can hear you, by the way. Yeah.
Okay, if the technology were to advance enough for the solid-state batteries to be incorporated in electric vehicles, could we expect like much more range and stability for these batteries?
Excellent. So when it comes to the range, one of the most promising thing about the solid-state batteries, remember that I showed you the lithium? We don't use graphite, we use the lithium just to have more capacity and to have also more voltage window to have more energy. Once you improve the energy density, you will have higher range, definitely. Will we expect in the electric vehicle? Of course, it depends on so many things. Technical aside, also we have the cost. The cost, of course, still is high. So I don't think the solid state will be like something ubiquitous like any lithium-ion battery. It will have its own niche, high-end application. But definitely, the promise is that for the solid state, it will have more energy, more range, and even safer than the current batteries. Okay, any more questions?
No questions.
We have questions. Oh.
No questions.
Okay, خلاص. طيب. Thank you very much. If you have any questions, please, you can find me. Okay, thank you very much.
Thank you, Dr. Ataf, for that eye-opening presentation. It's great to see innovations in the energy lead at NEOM. In his keynote titled, Innovating for the Future, How Additive Manufacturing is Shaping Sustainable Infrastructure, he'll be focusing on the impact of additive manufacturing in healthcare. Please join me in welcoming Mr. Mu'adh.
Hello, gonna say it straightforward. 2009, I've seen first 3D printer in university, was Waterloo University in Canada, and sadly my life just got changed. I took that route of additive manufacturing. It's crazy, it's huge. We haven't realized the grasp of manufacturing medical. I worked in the Royal Clinic, Mayo Clinic, I worked also in Cleveland Clinic. We jumped around to multiple clinics exploring 3D printing in terms of implantation, surgical guides, helping patients with cancer. But the question that I always get is 3D printing a luxury or something just, just one of the tools in a box? Or it's actually, my career was NEOM, it's the future city. So it's very huge responsibility in NEOM. I focus there on 3D printing of concrete. So my focus on actually building facades, 15,000 meters of facades to cover, for example, mountains. I focus on nature elements such as corals printing, 3D printing. You could jump around. You could go to printing food, fashion, I would say and medical implants. You could go anywhere if you want. So today I actually divided the session into two sections. I wanted to do it that way. So we will have a technical, quick review on the technologies of 3D printing, the most famous technologies, and then we'll jump right away on real world applications. I think this is what people love. Okay, talk been applied on a critical matter. That's what matters behind science. So let me take you just through a little bit of history. Let me jump here. Maybe the signal will kick. There. What is the, okay, I think this is a good spot. Again. Screen, perfect. Let's go back to the history. Any science discovery, I would say, or patent, or whatnot, start somewhere. So 3D printing, yes, the last patent was around 30 years old. It's even more than 30 years old. When we talk about 3D printing, it starts with papers, starts with actually science fiction. That's why science fiction actually really crucial in creating a lot of science, I would say, discoveries. We're talking about robots, AI, a lot of science, discoveries just comes out in a box of somebody who's trying to write science fiction, and suddenly it's realized as a science. So started in 1945 as a line in one of the science fiction novels, and jumps all the way to publications with Dr. Hayoto Kadima actually have done a great job in terms of publications. But what happened do you think? Why those scientists could not get the money out of the science? What happened is, if the science work, but you don't have the fund, it wouldn't move to commercialization, it wouldn't go to the market. But we have a lucky people, or Bill Master and Chuck, Charles, they commercialize it. He makes the first portable desktop 3D printer. And then after him came in 1989, Scott Crumb with another technology for 3D printing. And after this, 3D printing just got exploded, but got withheld for a few years because of patent. So 20 years of patent, we were just waiting, until after this 20 years, that's why you see exploding of 3D printing in the past, I would say 10 years. We have a lot of desktop printers, we have a lot of companies who's competing within this field. Yes, it starts from a garage, it's fine. Huge discoveries, multi-billion companies, starts from a garage. So what I'm saying here, I think a lot of discoveries need to start small, and it's okay to start small. It's okay to think big, but take it in gradual steps, and this is what happened with 3D printing. When people talk about 3D printing or additive manufacturing, they think of one thing, but you forgot that additive manufacturing actually it's a full spectrum for a lot of techniques and technologies. We're talking about liquid printing, which is wet photopolymerization, material extrusion, material jetting, binder jetting, each one of them different. One of them multicolors. One of them has this strength. Another one has this ability to be, for example, antimicrobial, antibacterial. Another material is actually printing with solids, like steel, and other techniques as well, even with paper. This is actually one of the really early stages of 3D printing and additive manufacturing. They have paper, and then you cut the paper, you bind it, you cut the paper, you bind it, until you have this big 3D printed element, which is very old method, was manually done as 3D printing. So I wanted to jump for each one of them. We go quickly, understand it a little bit, and jump to application. So wet photopolymerization, it's well known of SLA. I use it a lot in medical field. I use it in surgical guides, where we actually design customized guides that you use it, for example, close to the patient where he has or she has a tumor, where we actually cut. I will go back to medical at the end of the presentation, but the beauty of this, it's the softness. Let me actually have a video here that I can represent. Okay, great. So what it does exactly, have a dish that has liquid. This is liquid plastic, but it gets react to the ultraviolet light. So once the ultraviolet light actually will go interact with this liquid, with 1 millimeter, I would say, depending on the accuracy that we do have, it solidify. And then imagine the layer goes up, solidify again, up, solidify again. But it has multiple technologies. It could be laser moving, or it could be actually flashes. And the intensity of photons on the liquid will make it solidify each time, as you see in the diagram here. Let's go for the favorite, I would say, to the field, FDM, FFF, material extrusion. Why this is favorite to a lot of people? Because it's accessible, it's easy, it's cheap. A lot of people get this machine, which is, it's like a glue gun. You feed it in a roll of plastic, we call it filament. Just go around. I would assume everybody knows 3D printing here. That's how I'm getting off of this. So this was actually really good for people who start in entry level. As you have seen it before, and I think you've seen it a lot. This technology, by the way, got exploded as well with a lot of materials. So 3D printing, actually there's three main corners of 3D printing. First, either you advance the material, or either you advance the electronics and mechanical, or either you advance the software for 3D printing. And this is how 3D printing actually go up and down. And in the era that we have now, the main focus actually on the material. Let's go on next. So we're printing with material. Yes, it's cool. We've been doing a lot of experimentation, but once material jetting came to the market, it actually changed a lot of things, because now we can print one element that has elastic parts, that has dissolvable parts, that has transparent parts, that has multicolor. So multi-jetting, it is actually droplets of a material. It's the same liquid that we do have. Those drop will be dropped in organized matter, and then you do have the ultraviolet light to cure it, as we see here. But the beauty is, if you have a prototype that has multiple parts, that you wanted to have one element from one print without assembly, you utilize this. We use it a lot in medical simulation, where we have, for example, simulating muscles or nerves or whatnot. This will actually add a lot of benefits. Let's jump into the next technology, which is, would assume, today the clicker doesn't like me, I don't know why. This side, let's see. Even this side. Let's go up, okay. So binder jetting. We had multiple colors, multiple material before, but we wanted to explore all the colors. I want a photorealistic print, and this is where binder jetting jumps in. And a lot of models that you see for scale models, maquettes, for building, utilize the binder jetting technology. Let me show you how does it work. It's a container of a powder, and there's a lever that pushes just one layer of powder, and then you have the curing material to cure the thing. But this is a big leap. You see how we started? We started with liquid, one material, and then multiple material, multiple color, but limited color to 5 and 6. And then we jumped to full colors. But the issue with this, what is it? It's the actually structural strength. Yes, it does a full print without overhangs, which means we don't need to do a lot of post-processing. But with this technology, you could achieve a full product that fully colored. Let's go to other one, which is the jump, which is what I loved and I focused on for a long time. It's the powder bed fusion. Now we're talking about same mechanism, by the way. So always there's a container and there's a lever to push the material, but the curing or the binding mechanism is different here. We have a strong laser, whether it's a, electron beam melting, whether it's a selective laser sintering. So the sintering comes with polymer mainly. So you have a beam of laser that goes around, solidify the small particles together, and you have another powder layer, and the laser comes on, and then solidify the same layer as well until you go full on with full product. SLS is very beautiful, very amazing technology because it helps a lot with mechanical parts. Now we need the strength, we need structural strength. You need actually not to have it just a model or prototype. You want to put it inside a machine. So this is where we use SLS. For me in my practice, I use it in 2 ways. I use it in medical, cutting guides as well. We use it in simulated medical elements. As well, we use it in the guiding to place the implant inside the patient, as well for medical, for space actually applications. Because, let me give you an example. Now, if you want to ship something into space, what happens usually? Usually they will have a lot of boxes and they will ship them. But the boxes and the shape and the size to be shipped and placed inside, for example, the space station, this is a critical thing. They don't like to have a lot of, they calculate the millimeter on the International Space Station. So when 3D printing, what you do actually, you ship the material and they have a printer there. The material is a powder. So you can stack it the way that is small, contained in one area. But once you go there, you have a library of spare parts that you can just feed in the system and then print there without compromising the shipment. So this is for the SLM, selective laser melting or selective laser sintering. It's all under powder bed fusion. So when you get a product, the 3D printing product, usually we need to go a lot of filtering what we, the request that we get. We need to understand the functionality of it to select the material. Sometimes you get a request, but you want to understand what type of technology we just explained need to be selected. If we're talking about thermoplastic, we go SLS, selective laser sintering. Wallahi, if we need something that related to metal more, we go SLM, selective laser melting. If we are using something that needs lightweight and needs to have intricate details without supporting material, we go to binder jetting. So you have multiple ways to select a product. We have based on the function, as we spoke about, some technologies actually focus on things and some other technologies focus on other things. So we have technologies who focus solely on the shape and the beauty of the prototype, and there's other technologies focused on actually having a fully solid product. So as you see here, you see a lot of things from fitting to high strength to special property to flexibility. And based on those values, you go select what type of technology you should select to produce your part. As well here for surface appearance, because that's the issue with 3D printing. Try to imagine with me 3D printing. FDM, for example. You're printing, and then you cannot print on air if there is like an overhang or overarch, correct? So you need to create support material. And this support material, after you print it and you try to take it out afterwards, it's gonna have residuals. For example, for me in medical field, if I wanna do something that will help the patient, 1 millimeter, even microns, 50 microns is very crucial to me. So any residuals, I don't want to see it. That's why you select a material or technology that has a dissolvable part or has a style. For example, when we talk about SLS, selective laser sintering, you're printing within a powder. So you could create any complex shapes that you do have within the, the container of the printer, and you wouldn't have any residual because at the end you just need to de-dust it and clean the dust, and all the overhangs will be strong. Let's jump into application. Khalas, we finished the boring part. I wouldn't call it the boring part, but I mean, when we see the application now, I need you to make the correlation. So say, oh, this technology have done this technology have done that. And I think this is the way that we think about it. We need to think about how are we going to do those products? Because you're going to tell me now, Mu'adh, wait a second. I think SLS is better than FDM for this application. I think this is better than this. What I need you to get out of this conversation today, that understanding of the technology and its sub-technologies and techniques will help you a lot to select what's best to utilize for 3D printing. Because we've been focusing on single printing technique, missing out on a big spectrum that 3D printing have done. One of my projects, I'll just throw it there, was a rod that actually is dissolvable. So for example, if any of us, بعيد الشر, have a car accident and broke his leg. So what happened is they will put a rod, you will wait for the healing, usually 3 months, at least 3 months. But the issue is the rod is gonna still there in your leg, and you need to have another surgery to remove it. But what if you 3D printed something that you could insert there and then could dissolve after 6 months? So we utilize a material that based on sugarcane as well to implant, to make a solid implant strong that will support within the duration, and after a while it could dissolve and could goes away. I'll show some example coming up. So 3D printing goes in a lot of things. Education, obviously. I mean, learning from touching, from looking, it's much better. You could do it in product design, data visualization, engineering student. I bet you guys, you all, if you are in engineering or even another department, it has 3D printing a lot in visualization. And I bet you if you've seen it that way, not in a computer, and you assemble it yourself, your education level, your comprehending of the topic will be much better. Construction, which is my main role in NEOM, so I had the 3D actually construction within NEOM. We do a lot of work in construction, and I think by far, that's why I jumped from medical to construction. It's the most, I would say, commercially, the most, pushing technology that's gonna explode soon. So I'll tell you an example. You've seen NEOM, you've seen the renders, you've seen the pictures, correct? Have you seen just one boxy building in NEOM? Or all our building that we do have is bio-inspired always, has a really, intricate details or, for example, engraved things. How can you produce this within, for example, those years that we do have? For example, we have Trojena, it's coming up in 2029. We have Oxygen, 2026. We have, for example, the line, 2034. So there's a lot of dates that we do have, and you can produce such an intricate details of a huge area, except if you have something that has the flexibility to do so. But NEOM will have a responsibility of sustainability as well. That's also the beauty of 3D printing. So what do? You build a factory that has robotics arms, for example, for 3D printing, closer in the mountain, and then you choose from the local material, sand, aggregate, cement, admixtures, to do a whole 3D printing inside the mountain, because you're gonna take the facades from here, and then you're gonna install right away here. Because imagine shipping all this amount of panels and concrete all around the globe. We destroyed something called carbon footprint. We already destroyed before we build. So the idea of 3D printing is actually you contributing heavily into the sustainability storm. So I'll try to have some pictures also more. This is one of the actually main project that started. There's 100 homes been built in just 3 months in New Mexico. And due to 3D printing, flexibility, the printers can print and move. Print and move. This is a printer called Cobod printer. With Cobod has 32 by 12 by 8 meters. It's amazing printer. But as you see, you can see the lines. And this is what we're trying to see how people will adapt to those lines. Because still it's gonna settle there. Other companies, you know what they have done? They have 3D printer that you could print, and then they have another robot that could plaster and paint. So you had the full, the full, I would say, construction stages. I mean, Italian jump in the game. Italian have this taste. They want to play around with those lines, so they just added a little wave, and this wave added this pattern, which just looks amazing. By the way, those building doesn't have rebar, so you don't have a steel, you don't have anything, which is also an amazing thing to be added. We'll just move forward. You go to space. You want to send a lot of workers on space to build habitat, or you just want to send a 3D printer. You program it from away and then let it print on there. Also, multiple intricate shapes. This will be printed in multiple parts. Will be assembled on the place, and will be plastered and post processed. Jewelry as well, 3D printing engaged in jewelry, because jewelry you could print with wax, intricate details, and then you can make the cast out of the wax that you already printed. I just want to jump in a question. What do you think the technology that printed the wax? I never mentioned it, but I mean, there's one technology where I mentioned that we use it in medical. It's very crucial. It's actually the first technology is SLA, vet photopolymerization, because it goes to intricate details and levels. This is the outcome. Food, even food will be printed. So if you want to do mass, production of food, and you want to have it multiple shapes, it actually can be printed as well. I will jump fast as well. All what I wanted to tell you, that 3D printing can jump in a lot of areas. Pizza could be printed because it has layers, has dough, tomato sauce, cheese. Fabric and fashion can be printed. If you want to produce something that has repetitive fashion and shapes, they also can be printed in multiple intricate details. For space application as well, why printing in space is very important? Because space, they wanted to produce things on the side there. I think 3D printing can do that easily. If they can perfect it on land, they can perfect it outside. 3D printing merge with a robotics arm. If you want to build the biggest satellite to capture image outside, so you could utilize the printing on space as well. Let me jump fast. And this is where we jump into medical. Well, excuse me, I will take just 5 quick minutes onto medical. Medical basically, I think, is the very impactful, straightforward for 3D printing. We start by biomedical imaging, we analyze the images, and then we isolate the muscles from the nerve, from the bones, and then we do the planning. And then we create the implants and other software. We adopt the plan to the implant, and then we 3D print it. And then once you 3D print it, you 3D print an element that's actually, it's not going to be resisted by the body. At the same time, it's light. Some of you guys today working on, lattice manipulation inside the implants and whatnot. And it's applicable. It's been implanted in Saudi around 107 patients, 3D printed implants. But I think it's actually doing great job in terms of weight, because if you have a metal and not intricate, specialized, customized implants, you would have the patient afterwards. For example, we have the maxilla here. If you have an implant in the maxilla, the patient afterwards, you're going to see him tilting a little bit down within the long run. But once you have a peak, this is polyether ketone material. It's very light, corrosionizes the plastic because it's very, I would say the body would not reject it. Let's put it in simple terms. So let's have some quick example of the cases. So there's a lot of examples for cases. Let me take one of the most important examples that we work on. Let's take this gray skull, for example. This is a patient that came to me. This patient had a big, huge trauma, and then they needed to remove some part of his maxilla and actually a mandible. What happens is, you see the metal bar that we have there? Inside the OR, the operation, they actually bend the metal inside and then insert it into the patient. Every single minute in the operation room is actually counted for. So you're bending for 20 minutes, that's crazy. So what if we actually took the CT scan of the patient, 3D printed with good accuracy, bend the whole metals and rods beforehand, and we just gave it to the surgeon just to implant and screw it and just put it in space. And this will actually reduce a lot of time. We did multiple surgical planning. You have the patient. This patient has a severe cleft palate, which needed to do very complex surgery, actually. We measured the nerves even of the eyes if we're gonna, reduce the distance that's in the forehead. So they call it bictostomy surgery. So we did all the 3D printed parts. We gave it 10 models to surgeons. Surgeons practice multiple times, trying to twist the bones to make sure they are getting it right, not increasing the distance, until they get it right before the surgery. Once they enter the surgery, already they know exactly the movement motion they're getting at. Surgical training, there's a lot of things in training. It's been made to be fixed. You order something, all heart is fixed. It's the same exactly. But with 3D printing, you select a lot of, for example, congenital diseases in the heart, and then you 3D print them to replicate what reality look like. Because having a heart that ordered from online as a mass-produced, it's not going to replicate for you exactly what the patient actually face and has. So this is one of the examples of multiple cases based on real life examples. Prosthetics, obviously, prosthetics is a big thing. And 3D printing added a lot of work in prosthetics. We don't print the prosthetics right away, especially for the facial prosthesis. What happens here, you print the mold, and then you inject it with silicone. Other thing as well, the metal printing. Metal printing added a tremendous advancement in medical field, especially in an area that you cannot put actually polymer. For example, if we have a patient right now that has a tumor in their pelvis, and then you need to cut the tumor, remove it out, you think what they're gonna add instead of the pelvis area that been segmented? What is available today? It's crucial to know. There's nothing available today. They put like just metal rods, and they make a mesh, and they try to replicate whatever they can salvage. But with the 3D printing, we select exactly the area, the cuts. We take the half of the pelvis that ready, we mirror it to the left. We do the calculation of the weight, and then we 3D print a precise replica of an implant that will give, I would say, integrity to the patient at least. Surgical guides, one of the best things as well. Why we're letting the doctor decide where to cut exactly? We could calculate everything. We could do the surgical planning prior to the surgery. We put the surgery, he practiced in the computer, we understand exactly where the angulation, the depth, the slice, and then we produce surgical guides. And those surgical guides will be the guides for the patient, guides for the doctor and the surgeon, where he's gonna cut exactly, precisely without knocking a nerve or blood vessel. And that's where 3D printing surgical guides actually worked very well in a lot of, surgeries. Finally, at the end, I wanted to speak and end up with bioprinting, because this is what's gonna actually change a lot in medical field. We do a lot of experimentation with bioprinting. It's been successful in some cases. In 2022, collective researchers led by Dr. Anthony Atallah have printed a cartridges, like 4 millimeter of cartridges on space. Don't ask me why on space, but I'll tell you why. That could actually, change the way that we think about, implants and transplants as well. So printing on space, why? Because, when you print, you're adding layer above layer. So by printing, you create a scaffold and then you print by adding droplets. When you add a drop, like the bio ink, on top of another drop, you have the gravity of Earth. And the gravity will smooch those two parts together. So what happened on space, they create a space printer, which is, imagine that you have a sphere, okay? Just try to imagine with me. And inside the sphere, you have multiple magnets that you will be able to control the magnetization. So you drop, and then you have the magnets to move where the drop is, and then you add the second drop, third drop. So you're printing and controlling the movement and the position of the bio ink by the magnetization inside the sphere in a zero gravity status, which is a space. And this is to allow the integration between each bio ink together, which is crazy, I think, and I think it will increase a lot what we think about medical now. I mean, we might cancel something called implants. If somebody actually wanted to follow up on this project, I would say you follow Dr. Anthony Atallah. He's one of the pioneers. He's been working on this project for 20 years. Thank you so much for listening and taking time.
Thank you, Mr. Mu'adh, for that incredible presentation.
Yeah, what an incredible day it was, and continued with the same excitement, enthusiasm, and interest of day one. We want to thank our speakers and, more importantly, you for making this day a very wonderful and memorable day.
It was truly amazing. Thank you all for your attendance. And now it's time for lunch. Keep the conversations going and use the most of this opportunity to network with other attendees. And don't forget to visit our exhibition in Building 54. It'll be opening at 12:20 today.
And don't forget, Jisr continues. We have day 3 waiting with more exciting sessions ahead. Thank you again, and we hope to see you all tomorrow.
Thank you.